Alright, so adjugate of a matrix. Suppose you're given this matrix A11 through A33, and we define the minor as Aij as the determinant of the smaller matrix the minor will be the determinant of the smaller matrix obtained by taking the elements, column and the row out. You get a smaller matrix, right? You take the determinant of that, that's called the minor, right? So to get the adjugate, you have to perform 3 steps. First is, step 1, replace all elements by its minor. Step 2, apply the checkerboard of signs. So you remember this checkerboard, right? So things that are in the pluses, you leave it, but then things that are on these positions, you negate it. So what's positive will be negative, what's negative will be positive. And then step 3, take transpose. So that with respect to diagonals, diagonals stay in the same place, but then these two flip, right? That's transpose. If you do that, you get the adjugate of a matrix. And the significance of this is, you know, if you take the determinant of the given matrix, then when you do the row expansion, right? When you do the row expansion, it's A11 times this minor, right? So it'll be capital A11 minus, because of the checkerboard of signs, A12, capital A12, and then plus, again for the checkerboard of signs, plus minus plus, A13, capital A13. So that's how you write down the determinant, and you can see that when you multiply the adjugate of a matrix A, well, what is this? According to this definition, it's like, it's A11, A1, A22, A33. That stays the same, but then instead of A12 here, the A12 will go over here. A21 will, these two will be switched because of the transpose. Same thing here. It's instead of A32, I'll put A23, A32. Then this one will be A31, and this will be A13, right? So if you take this, and if you multiply, this is the adjugate of A, if you multiply the original matrix by this one, oh, and I forgot to put this signs, checkerboard of signs. So that's the adjugate of the original matrix. And then if I put A11, A12, A13, A21, A22, A23, A31, A32, A33, if you multiply like that, then you get exactly this that we wrote down, right? So what does that give you? It gives you the determinant of A on the diagonal. So on the diagonal, you'll get exactly the determinant of A. Now, note that determinant of A is a number. It's not a matrix. So these are numbers. And then, if you look at what happens if you multiply this with this, this times this will actually be same as A12, A22, A32. No, that's not what I want. Sorry. Okay. See, what I wrote before would be true if I switch these two around. But now I can think of this. This times this will be exactly same as the column expansion, 2, 1. Right? It's A11, A11, A21, A21, A31, A31. Exactly same as this one, right? So again, for the same reason, it will be determinant A, determinant A. That doesn't change. But then if you did this times this, that quantity will be the same thing as determinant of A12, A22, A32 with A12, A22, A32, A13, A23, A33. It will be same as this determinant with column expansion this way. You can check that if you did the column expansion this way and you wrote down what you get, it's exactly same as the formula you get if you did this times this. But look at this. This is like the original matrix determinant where the first row is now replaced by the second row. The first column is replaced by the second column, right? And if you have the same column, what happens? The determinant is, if you have the same column, then the determinant is, you remember the row operations or column operations, right? So you can take any column, multiply, you can take any multiple of one column added to the other, and the determinant doesn't change, right? So if you take -1 of this and add it to the second one, making this entire thing a 0, the determinant doesn't change. But if you have an entire column as 0, then the column expansion with respect to that will give you 0, right? So what you know is that if you have any determinant that has the same row or same column, then automatically that determinant will be 0. So that will happen for every one of these so that it will be 0 here, 0 here, 0 here, 0 here, 0 here, 0 here, so that this will be determinant of A times the identity. And this observation leads you to a very nice formula for the inverse. So you end up with the formula for the inverse. That's the point about the adjugate. So if you have a matrix like this, then the formula for the A inverse is 1 over the determinant of A times the adjugate of that matrix. That's what it is. And although I only wrote what happens when you have a 3 by 3, you can define adjugate of a matrix, any square matrix, by just following those rules, the 3 steps. So adjugate is defined for any n by n matrix, and determinant is defined for any n by n matrix. Therefore, this formula is valid for anything. Okay? And why do we want this? Well, we want it because if you have any equation like A11 times x1 plus A12 times x2 plus A13 x3 is equal to B1, and that A21 x1 plus da 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 da, and then A33 x3 is equal to B2, B3. If you have that, then you can rewrite this as matrix A times x1, x2, x3 equals to B1, B2, B3. And you can solve this by multiplying the inverse to the other side to get the answer. Now at this point you might ask, well, why use this method when you can just do REF? REF is much easier with a calculator. And my answer would be, well, you can only do REF easily if all the coefficients are numbers, right? Once you have some letters in there, then doing REF is very confusing, right? So you probably have seen this if you took engineering statics. So in engineering statics, if you have like 3 forces on a diagram, you might end up with like questions like, oh, I have m of F1 plus capital M of F2 plus just F3 equals to 0, something like that, right? Then in the next line you might have something like m plus capital M times F2 plus 2F3 is 1. And then let's say you have F1 minus 4F3 is 2. Suppose you were to solve an equation like this. Then trying to solve this with REF is a nightmare. You probably don't want to do that. Okay? But then, trying to solve this with this is also a nightmare as well. Okay? And that's why some smart mathematician named Cramer looked at this situation and came up with a simpler expression for the solution. Right? So, let's talk about that. Okay, well, let me first give you the solution using the Cramer's rule, and then explain what Cramer's rule in general, why it's true. Okay? So, Cramer's rule says if you want x1, you have to, let's first write down the equation and then we'll apply the Cramer's rule. So what's the matrix here? This is M, capital M, 1. The coefficient matrix is 0, M plus M, and 2. And then it's 1, 0, negative 4. Okay, times x1, x2, x3 equals to 0, 1, 2. So that's the equation that we have to solve. Let me write down the solution in terms of the Cramer's rule. The Cramer's rule says the solution x1 can be written as ratio of two determinants, where the determinant in the bottom is always the same. It's the determinant of the given matrix. It's M, capital M, 1, 0, M plus M, 2, 1, 0, negative 4. On the other hand, the top one is you take the very first column. For x1, you take the very first column and replace by the column matrix B. Okay? So you replace the very first one by 0, 1, 2. Rest of them stays the same. Okay. Let's do the calculation, right? So let's do row expansion this way. Let's see what that gives us. 0 we don't have to write, so it'll be negative m times m plus m and 2 and then 0, negative 4 plus 1 times 1 m plus m, 2 and then 0 divided by, and if I do, it's good to have some zeros, so let's do this. Column expansion. So m times m plus m, 2, 0, negative 4. And then plus, the zero doesn't count, so it's plus 1. Capital M, 1, m plus m, and 2.
Okay, how are you?
All right, so let's continue on. What is this? This is just negative 4 times negative m, so it's 4 capital M, m plus m, And it's 0 minus 2, so it's minus 2 m plus n. And then down here, this is negative 4m, m plus n. And then 2m minus, this will be plus 2 capital M minus m minus n. So let's simplify. I see that these two are common, so it will be 4 capital M minus 2 times m plus n. Whereas in the bottom, you can't do anything else, so let's just leave it as it is. So it will be negative 4m, m plus m, plus capital M minus small m. Because 2m minus m is just m. So that's what we have for x1. Now, for x2, what should we do? x2 is exactly the same idea. The denominator will be the same exact denominator, which is that one, that ugly thing, negative 4m, m plus n, plus capital M minus m. On the other hand, the top will be the same determinant, except now the middle one is replaced by 0, 1, 2. So it will be m 0, 1, 0, 1, 2, and then 1, 2, negative 4. Okay? And then if I expand this way, it will be m times 1, 2, 2, negative 4, plus 1 times 0, 1, 1, 2, over negative 4m, m plus m, plus capital M minus m. As negative 4, another negative 4 would be negative 8m, be 2 minus 1. And then finally, x3 would be m0, 1, capital M, m plus m, 0 with the last row now replaced by 0, 1, 2. Okay. Over the same thing as before. And this one would be m plus n. I'm doing the row expansion as before, okay? Then 2, 0, 1 minus capital M 0, 1, 1, 2 over the same thing. And it will be 2m m plus m minus, actually plus capital M over negative 4m m plus m plus capital M minus m. Okay, so that was very tough, but imagine doing the same thing for R and F. It would be very, very hard. Okay, so this is still better than having to do R and F in this context. And I probably already explained what Cramers rule is, right? You just, if you have AX equals to B, just replace each one of these columns by this, one by one, and then divide by the determinant of the entire matrix. That gives you the value. That's Cramers rule. Now, I purposely did a harder example here, but for the exam purposes, I can put more zeros and the numbers will come out to be easier than what I have here, okay? So A22, A23, A31, A32, A33 times x1, x2, x3 is equal to B1, B2, B3. Let's say that's what we're trying to solve. Okay? Then I already know that the inverse function, what's the solution of this? I can multiply A inverse both sides. this will cancel and you get x as A inverse of B, right? So if you know the A inverse, then you have the solution right away. And we do know the A inverse. It's given by the adjugate, right? So what's the solution? x1, x2, x3 is equal to 1 over the determinant of A times the adjugate of A. That's A inverse. This much is A inverse. We talked about that, right? Let's see if other markers better. And then you have times B1, B2, B3. Okay? So that's going to give you the solution. Let's write down the full adjugate. So I'm just going to rewrite the determinant as 1 over determinant of A like that. And then over here, the entire thing is, adjugate is, as you see, it's A11, A21, A31, because there's a transpose involved. You see that it's now, this should really be a column, but I'm writing it as a row. A12, A22, A32, and then A13, A23, A33, with the checkerboard of signs applied, multiplied to B1, B2, B3. Okay. And then I explained what, say, A22 means, right? A22 means you take A22 and then delete the column and the row containing that, and you get a small matrix. The determinant of that small matrix is what we call capital A22, right? So that's the minor of the matrix. So that's your adjugate. And now look at what's happening. This is this times that. That gives you x1. So if you read off what x1 is, just by doing the matrix multiplication, right? It's across down, right? So if you do this times this, you get x1 as 1 over A times B1 times A11 minus B2 times A21 plus B3 times A31. But then that looks exactly like a matrix expansion, isn't it? What matrix would this be? Well, it will be the matrix where it's exactly same as this matrix, right? So you have A11, A12, A13, A21, A22, A23, A31, A32, A33. But this first one is replaced by B1, B2, B3. And you do a column expansion, then think about what you get. B1 times this, what's that? This is exactly A11, isn't it? So you get B1 times A11, which is exactly this one. Right? And the next element will be minus B2. Minus comes from the checkerboard of signs, right? And B2 times, delete the row and the column containing it, and then you get these two things, minor. What's that? That's exactly A21. So that's exactly this. And then you have B3A1, A31, but that's exactly B3 times the determinant of this. That's exactly the same as that one. So you see that this determinant captures exactly this quantity, and that's where the Cramers rule comes from. This is exactly the Cramers rule, isn't it? Right? Yeah. You replace the first column by B1, B2, B3. And you can work out the other ones to verify that in fact, x2 can be obtained by taking the second column, replacing it by B1, B2, B3, taking the third column by B1, B2, B3. Okay? So that's what you do. That's all.